Hi there, and welcome to our lecture on work and power. This is Energy 1 of Unit 7. Our key ideas: how is work calculated? What's the relationship between work and power? And then how do machines make work easier? Alright, so looking at this first question, work is just calculated by multiplying the force that is applied to an object and then the amount of distance which that force is applied. So whether we're lifting something or setting something down or pushing it across the floor or pulling it across the floor, as long as we're applying a force and it's moving some distance, then we've got work. At least in the sense of the physics definition or science definition, this is how work is defined. And we do have a mathematical formula that's attached to this. So work equals force times distance, or big W or capital W equals F times D, where work is measured in joules, force is measured in newtons, and distance is measured in meters. And we'll look at a problem here in just a little bit. Alright, so force must be applied in the object's motion for work to be taking place as well. So we're applying a force, that object needs to be moving in the direction of that force for us to be doing work on that particular object. Alright, so we can define work as a transfer of energy to an object by the application of a force that causes the object to move in the direction of the force. So work is zero when an object is not moving, so we can push on something all day, or we can hold a stack of books in our hand. If they don't move from their location, we're not doing work. And again, work is measured in joules. And 1 joule is equal to either 1 Newton times meters, or 1 Newton meter, which then we can break newtons down into 1 kilogram times meters per second squared. But because newtons, we have 1 Newton times meters, then our meters become squares, so we end up with 1 kilogram times meter squared divided by second squared. Just know if you're ever asked to find work, you're going to use the joule, so you really don't have to worry about this really big this really big unit. Just know that I'm asked for work, I need to put joules down. Alright, so we'll look at a little problem here. Imagine a father playing with his daughter by lifting her repeatedly in the air. How much work does he do with each lift if he lifts her 2 meters and exerts an average force of 190 newtons? So we're going to list what we know. We've got a force of 190 newtons, distance of 2.0 meters, and we're wanting to know work. So work is our unknown. So we can put our equation down here as work equals force times distance, or W equals F times D. And actually, when we rewrite the equation, this F should be a capital F and not a lowercase f. We tend to use a lowercase f with friction. Not really a big deal for us, but when we plug in this information, then our force is 190 newtons. We went a distance of 2.0 meters. So what we did is 380 Newton meters, newtons times meters, but this is going to change to joules. So just this N times M becomes J, capital J. Alright, so power. What's the relationship between work and power? Power is the rate at which work is done, or how much work is done in a given amount of time. So with power, we are doing work, so we have force applied over some distance, but to figure out how much power is taking place, we need to know how long that distance or that force is applied over that given distance. And again, another equation, our power equals work divided by time, or P equals W divided by T. So define power, a quantity that measures the rate at which work is done or energy is transformed. We measure work in watts, so we have joules per seconds, or joule per second. we just convert that over to a capital W, or watts, and here we've got the information written out. So work is measured in joules, time is measured in seconds, and we just change joule per second to the watt. Alright, so lifting an elevator 18 meters takes 100 kilojoules. If doing so takes 20 seconds, what's the average power of the elevator during this process? So we're going to list what we know. Work is equal to 100 kilojoules, which we can change to 1 times 10 to the 5th joules, or 100,000 joules. Our time is 20 seconds, and our distance is 18 meters. But since we're not calculating work, or we're already given the amount of work that's done, the 18 meters really doesn't make much difference because it's already been utilized in the problem. So then we want to calculate for power, and we're calculating power in the unit of watts. So our equation, power equals work divided by time, or P equals W divided by T. I'm going to insert what we have. We've got work is 1 times 10 to the 5th joules. This takes place over 20 seconds, so we end up with 5 times 10 to the 3rd joules per second, or 5,000 joules per second. And joules per second changes to watts. And then if we wanted to get rid of this times 10, we could divide watts by 1,000 to give us kilowatts. So we have 5 kilowatts in our example. All right, last thing we're going to talk about is machines and mechanical advantage. So how do machines make work easier? Machines help do work by changing the size of an input force, the direction of the force, or both. So this is an important ratio for figuring out how efficient a machine may be. So mechanical advantage we define as a quantity that expresses how much a machine multiplies force or distance. So we have an equation for this one as well. So this is our third equation for this particular section. Mechanical advantage equals output force divided by input force, which is the same, or we could, instead of doing output force divided by input force, we could do input distance divided by output distance. So we could use either forces or distance depending on what we have and what we're wanting to find. All right, so an example problem here to calculate the mechanical advantage of a ramp that's 5 meters long and 1.5 meters high. So we're going to use the distance part of the mechanical advantage equation. So input distance is 5 meters. Our output distance is 1.5 meters. So our mechanical advantage is what we want to find. So again, we only need the distance part of this full equation. So mechanical advantage equals input distance divided by output distance. So we're just going to plug in our values. So mechanical advantage is 5. Input was 5 meters divided by 1.5 meters. So the meters cancel out, so our mechanical advantage is just a number. There's no units associated with this since they canceled out. Another thing I want to point out here is, say this was, what was our original problem? Oh, we're talking about a ramp. So even though we are pushing up the ramp at 5 meters up this 1.5 meter incline, our mechanical advantage is 3.3. So, thanks for listening.